Good morning, everyone. Today we will talk about a very interesting topic which is called the exponential of a matrix. So welcome to classroom. Let's start with some basic definitions or some things that you are already familiar with, which is called the exponential function. You know the exponential function is defined in the complex plane into the complex plane, and it is a bijection from this to this set. This is a bijection. So you know how this is defined. This comes here. This is just notation, and this is equal to so this is not being circular, I mean this is the real exponential function, and this is the complex exponential. So there is no circular reasoning here, and this is of course since zeta is a plus iv. Yeah, now this makes sense. And since a and v are both real numbers, a and v are real numbers, then this is a real exponential, and this is the cosine of a real number, which is b. So this is the real cosine, and this is the real sine. I mean, they are real because in complex analysis we have complex cosine and complex sine, in general complex trigonometric functions, right? So this is how the exponential function is defined. Let's say the complex exponential. So from here we will this will motivate us to define the main topic of today's video, which is matrix exponential. So how do we do this? Well, you know that the complex exponential function can be written in terms of its Taylor expansion, which goes like this. Then the first few terms will be zeta like this, factorial of 0, zeta square, cube, and so on. So we agree that this is the number 1, this is also the number 1 by definition or by convention, and so this will be, this is also 1, plus zeta square divided by 2 plus zeta cube divided by 6 plus zeta. So this is the Taylor expansion. We will write this quick Taylor expansion, and it makes sense for every complex number. Why? Well, the reasons are will not be covered here, but let's say you have the complex plane. Is a complex plane. For every point of the complex plane, let's say zeta sub 0, zeta naught, there is a neighborhood, there is a disk in which you can define this Taylor expansion. And by that I mean that the series converges. So this series is convergent, and outside it doesn't converge. So outside it doesn't make sense to talk about this series. Inside the neighborhood it converges, which means that we can have this infinite sum. So the thing is that for the complex exponential, this radius of convergence is infinite. So the neighborhood that we take will cover the whole complex plane. So to make things easier, we take theta naught to be the center of the plane to be 0, and so you can write it like this. This is very compact form. So the Taylor expansion has a radius of convergence of an infinite radius of convergence for the complex exponential, and since this is the case, we can define the complex by its Taylor expansion. So the complex exponential has two definitions. Quotation marks two definitions. The first one, which is the original definition, and its definition by Taylor expansions. So this definition of by Taylor expansions will motivate us to define the exponential of a matrix. So instead of exponentiation of zeta, we will exponentiate a matrix M, which is M is a matrix in this vector space. It is not the complex vector space, it's not, but here, oh well, at least at this level, we will start by these matrices with real coefficients. So these will be defined by this series, which is exactly the same as with the complex exponential. So the first few terms will be, of course, this one, also this one, plus, and you know, what follows, right? So we need some conventions here. Once again, you know that the factorial of 0 is equal to 1, but this matrix we still haven't decided what does this mean. So let's say that this is the identity matrix. Of course, this is the same matrix M, this is M times M, and so on. And every term here is a scalar, in this case a real number, no? It is a scalar. So there's nothing weird going on here. It's just a sum of matrix of the matrix I plus the matrix B plus 1 divided by 2 for the matrix M squared plus M cubed, and so on. The obvious question is, where does this series converge? So this is a question. Where? You know that for the complex function, the complex exponential, I mean, it converges in the whole plane, in the whole complex plane. So we now want to know in which part of this vector space of the vector space of matrices, let's say in which subset this makes sense. So it is not an easy question. It is, in fact, it obviously has an answer. Otherwise we will not be talking about this here. And the answer is that it converges once again in the whole space, in this case in the whole vector space. So it is very interesting, and this is in fact a very technical result. It requires a lot of lemmas, a lot of propositions, so we will not cover these the proof of convergence here. So let's accept that this in fact converges for every matrix M, and so. So this is then our starting point to solve a systems of differential equations. Why and how? Well, first, you know that for let x be a function that is defined from an open set of the real numbers into the real numbers, which is differentiable, then you have this linear differential equation with initial value. This is a Cauchy problem or an initial value problem. You know that the solution of the system of this initial value problem is a function like this. You know that this is the exponential, in this case the real exponential, right? So now in systems of linear equations like this, for instance, with some initial values, of course. So now you have a system of linear differential equations, and we wish to apply something similar to this, some exponentiation, and this is why we define this exponential of a matrix. Then to apply this exponential of a matrix, of course, you need to define a matrix. So the obvious step is to write this in its matrix form, like this, times a matrix A, let's say A. This will be a vector, the derivative of a vector times, which is x. And the matrix A will be 1, 3, 2, 1, of course. So now you have, this is equivalent which is this vector. Yeah, you have now linear differential equations, and just like before, the solution of this system, or well, of this initial value problem will be in terms of the exponential. So now this is a matrix, this is a vector. The result, of course, a vector. So it makes sense, right? The problem is, the obvious problem once again, is that to calculate the exponential of t times the matrix A, you need to calculate this infinite sum, which is not trivial. Of course, there are matrices for which this series is very easy to calculate, just to see that this is not entirely difficult. For instance, the most obvious one will be, what if the matrix A is the zero matrix? Then the exponential of A will be the exponential of the zero matrix, and this will be the infinite sum of from 0 to infinity, and this will be I, the identity, plus and so on, and of course this is 0, so this will be the identity. So the solution, let's say that this most trivial solution is the identity times the initial values, so this will be just initial values. Yeah, very easy. We didn't even know about this exponential, but there are more interesting problems in which it is completely necessary to do this by the exponential of a matrix, because in some cases you can do some algebraic tricks to solve these equations like this. I will give you now an example in which it is not required to know anything about the exponential of a matrix. Let's say this is k1 and the initial value of the second unknown is k2. You have this system which is equivalent to, let's say, just this derivative time x. Yeah, you could do this by the exponentiation of this matrix, but also you could solve this by solving this equation first, because you know that this is it is a Cauchy problem. You have a solution which is k2 times this, so you replace this here and you will have non-homogeneous linear differential equations, this one. So you know how to solve this. You identify this as a function pt is equal to -1, and this will be qt, and the solution will be then in terms of the integral of this one, and you know what follows. So you solve this without the need of the exponentiation of a matrix. So yes, you can do that, but there are cases in which it is not possible to do this by algebraic tricks. It will be very time consuming. So instead of doing all this algebraic work, you can just use the exponential of a matrix, and it will be very more fast. Your calculation will be faster with this. So to do this, we need some properties, of course, of the exponential of matrices, which will be covered in the following video. And you will need to review some concepts of linear algebra, because we will not exactly calculate the exponential of every matrix A, but the exponential of its Jacobian form. So you will need to review that. And so this will be it for today. If you have any questions, you can write it down in the comments. I will try my best to answer them as soon as possible. And if you have any topics that you would like me to cover, you can also write it in the comments, and I will try my best to work something about it. So see you around.